In this video, we'll discuss solution methods for nonlinear systems of equations. These will extend on the open methods for solving nonlinear equations that we developed in Chapter 3. We'll discuss two methods for solving systems of nonlinear equations. The first is called Newton's method, in which we linearize the equations near a solution and use a method for solving linear sets of equations. This is analogous to Newton's method for a single equation. We'll also discuss an extension of the fixed point method, which we developed for a single equation, and we'll use the fixed point method for solving systems of equations. To begin with, consider a nonlinear set of equations in n unknowns. In order to have a solution, we must have n equations for our n unknowns. These can be formulated as implicit equations. Then we select an initial guess for the solution vector, containing a guess for the values of each of the unknowns. Next, we perform a Taylor series expansion for each equation around that initial guess. And we keep only the linear terms. So we have a Taylor series expansion for f1 that says that f1 at x is equal to f1 at our initial guess for the solution, plus the sum over the partial derivatives of f with respect to each of the unknown variables, multiplied by the difference between that variable and the initial guess. Since the vector x represents the solution, then f1 at x on the left-hand side of this equation here should be equal to 0. We then define the difference between the solution vector and our guess for the solution vector as delta x. The elements of the delta x vector are delta x1, delta x2, etc. through delta x sub n. Those delta x's are the values multiplied by the partial derivatives in the first-order Taylor series expansion. We can write similar equations for each of the other n equations, f2 of x through fn of x. Then we write these equations in vector and matrix form. The first row of this equation represents the first-order Taylor series expansion of f1 around our initial guess. The second row represents the first-order Taylor series expansion of f2 around our initial guess. Note that all of the elements of the coefficient matrix on the left-hand side are partial derivatives of our nonlinear equations, each evaluated at the initial guess for our solution x1. So these elements are all constants. Also, the vector of functions on the right-hand side represent evaluating each of the functions at the initial guess, so these are also constants. This matrix you might identify as the Jacobian. This Jacobian is a square matrix because it has n rows and n columns. It's the Jacobian of our function vector f sub n. For Newton's method for systems to work, the determinant of this Jacobian has to be non-zero. That is, this Jacobian must have an inverse. Newton's method is a technique for converting a system of nonlinear equations to an approximate system of linear equations. So we choose our initial guess for the solution vector x. We find the values of f1 through fn at that initial guess, and we also compute the values of each element of the Jacobian matrix at the initial guess. Then we solve this linear system for the unknowns delta x1 through delta xn, which make up our vector delta x for the first iteration. For step 3, we can use any of the methods that we've already talked about for solving linear systems. Then, recognizing that delta x1 is the error on x1, we update our guesses for x by adding delta x1 to our initial guess from x1 to get our second guess, x2. Now, because the Taylor series that approximated nonlinear equations using only the first-order terms in the Taylor series expansion, x2 is also not an exact solution. So we iterate over steps 2 through 5, essentially using an extrapolation of Newton's method for a single equation to solve Newton's method for multiple equations simultaneously. The convergence of this method is not guaranteed. Just like with Newton's method for a single equation, our function f must be continuous and have continuous partial derivatives near the solution because we have to compute the Jacobian. Furthermore, the Jacobian must be non-singular. This is required in order for this matrix vector equation to have a solution. Finally, the initial guess must actually be near the actual solution for Newton's method to converge. Just like we can extend Newton's method for nonlinear equations to systems of equations, we can also extend the fixed point method for nonlinear systems to systems of equations. Beginning from the same implicit equations, f1 through fn, we need to rewrite each of these using an appropriate iteration function. That is, we solve for x1 as a function of all of the other x's using f1, and we solve for xn as a function of all of the other x's using the iteration function g sub n. We do that for each of the unknowns, using one equation for each of the unknowns. Then we rewrite those in vector form. So the vector x is equal to the vector of iteration functions g of x. Then we start with an initial guess x1, evaluate our vector of iteration functions to obtain the subsequent guess x2, and we continue until the solution converges. For the fixed point method to converge, g of x and its derivative must be continuous near the solution. And the initial guess, just like with Newton's method, must be close to the solution. Recall from Theorem 3.1 in Chapter 3 that the fixed point method for a single equation converges if there is a constant k less than 1 for which the absolute value of the derivative of g near the solution is less than k. For multiple equations, we have a similar constraint, but it's even more strict. In this case, the absolute value of each of the partial derivatives of g with respect to each of the unknowns x must be less than k divided by n for a system of n equations and n unknowns. In Chapter 4 of the methods text, we've discussed solution methods for systems of both linear and nonlinear equations. When all of our equations are linear, we can use either direct methods such as Gauss elimination or the LU factorization methods, or we can use iterative methods. The iterative methods tend to be faster for large systems of equations. These include the Jacobi and the Gauss-Seidel methods. In the LU factorization methods, we decomposed the coefficient vector A to a product of two matrices, a lower triangular and an upper triangular matrix. And that decomposition is the difficult step of the LU factorization methods. Then we solve for the unknown vector x by a combination of forward substitution and back substitution. In the iterative methods, we decompose the coefficient matrix A to a difference between two matrices, Q and P. The iterative methods have known convergence criteria. We also talked about ill conditioning, which is a situation in which small changes in the values of one or more of the coefficient matrix elements result in large changes in the solution. An ill-conditioned system can be difficult to solve using the iterative methods. Finally, we introduced two methods for solving nonlinear systems of equations. These were simple extensions of the open methods that we studied in Chapter 3 for a single equation, and include Newton's method and the fixed point method. Newton's method is performed by calculating the derivatives of the equations with respect to each of the unknowns and formulating what's called the Jacobian, and then using a first-order Taylor series expansion to linearize all of the equations. The fixed point method requires finding a suitable iteration function representing each of the equations in our system solved for one of the unknowns. Both Newton's method and the fixed point method are iterative methods for solving nonlinear systems of equations. They enable us to find solutions even when the equations can only be written implicitly.